So now our goal is to find a similar transformation equation so that we can start with x and t and find t prime. And I'm going to do this differently than how it's done in the spiral physics book because I think this way is a little more rigorous. I'm going to start off with this equation and I'm going to plug it into what I have here. So that gives me, I think I'll actually do this on a different page. So I have x is equal to gamma times x prime, but x prime is equal to gamma times x minus ut. I didn't need that extra parenthesis there. And then I have plus ut prime. And then my goal is to get an equation like this, but for t prime. So I want to solve for t prime. So I need everything else over on the other side of the equation. So first let's distribute all the gammas that we have. So it would be gamma squared times x minus gamma squared times ut plus just one gamma times ut prime. Then every term without a t prime is going to go over to the other side of the equation. So I have x minus gamma squared x plus gamma squared ut is equal to gamma ut prime. But now I have a problem because I have gamma squares and I have gamma, but this term doesn't have any gamma or gamma squares being multiplied by it. So we're going to fix that by multiplying x by gamma squared over gamma squared. We can do this because gamma squared over gamma squared is equal to 1. But rather than keeping it this way, I want to say, well, 1 over gamma would be equal to the square root of 1 minus v squared over c squared. So this gamma squared that I have in the denominator would be equal to 1 minus v squared over c squared in the numerator. Except that in general it was the velocity v, but for this situation that relative velocity would be u. So this would be gamma squared times 1 minus u squared over c squared. Okay, so I'm going to multiply x by this because this is just equal to 1. So now I have, let's actually do this over here. So if I do x times gamma squared times 1 minus u squared over c squared, then I want to distribute the x and gamma squared, so this is equal to x times gamma squared minus x times gamma squared times u squared over c squared. Okay, so then I can go back over here and I have x gamma squared minus x gamma squared u squared over c squared minus gamma squared x plus gamma squared ut is equal to gamma times ut prime. Now, with luck, things will cancel out. So x times gamma squared minus gamma squared times x, that gives me 0. And then if I look at everything I have left, actually let me just rewrite it. So I have minus x gamma squared u squared over c squared plus gamma squared ut is equal to gamma times ut prime. So there's a factor of gamma in every term, so we can cross out one of those, and a u in every term, so we can cross out one of those from each term. And now let me bring the t prime over and write it this way. T prime is equal to, this is gamma times t. This has a gamma in also, so we can pull that out front. This is just t, and this is minus, I already pulled out the gamma, so that's x times u divided by c squared. I think in the book they write it as u times x divided by c squared. And this is going to be the last equation that we need to complete the transformations. And that is exactly what they have down here. So this one is for going from the unprimed coordinates to the primed coordinates. So t prime is equal to gamma times t minus ux divided by c squared. Okay, so these four equations are a set of equations which allow you to take the coordinates of an event, which would be position and time, so 3 coordinates for position, 1 coordinate for time, so for an event in the unprimed frame, and find the corresponding coordinates in the primed frame. And then we have another set of equations, and the y's and the z's are very easy. You just write it the other way around. So z is equal to z prime. And then for the final one, you can change all the primes to unprimes as long as you change the sign of the velocity. So this would be t is equal to gamma times t prime plus u x prime over c squared. So you really only need to remember one set of these four equations, and I mean the y and the y prime and the z prime aren't really a big deal. So if you can remember these two equations, you don't really need to have these equations written out. As long as you remember to go the other way, you just change the primes to the unprimes and change the sign of the velocity. So these are the Lorentz transformations. And they're nice because they allow us to go back and forth between the reference frames. And maybe we don't have to think so hard when we use the equations as we did when we did length contraction and time dilation, because with time dilation we first had to identify the reference frame in which the proper time was being measured. We don't have to worry about that here, although you do have to make sure you know what the equations are actually spitting out. So you're putting coordinates in, it's spitting other coordinates out, but you do have to be able to interpret those correctly, which might be harder than you think. So we have our Lorentz transformations here, but the next problems that we have to look at in the book are not problems using the Lorentz transformation equations. They're actually problems using velocity addition. So we are going to use these, but we're not going to use them quite yet. So first we're going to do velocity addition, and then after we do those example problems, we'll go back to the Lorentz transformation problems. But we needed these equations in order to derive velocity addition, and that's what we're going to do next.